those microstates will have 0 entropy, right? Yeah. But that's what's that would be kind of useless. That would be totally useless, right? Yeah. So I think that even the people who are saying, "Oh, no, entropy can't depend on us. It can't depend on what we know about it. It can't depend on how we can manipulate it." If what they're using as their notion of entropy is Boltzmann entropy, it starts with a division, a dividing up the set of possible states into macrostates. And you asked right the question, well, what is a macrostate? Okay. Now, one thing that people often say is, well, look, there's certain variables that we're going to be measuring, macro variables, and our measuring instruments are going to have a certain range of precision, and a macrostate is a set of microstates that are indistinguishable according to the measurements that we're going to do. And then it's not there in the fundamental physics because it's relative to some set of it's relative to some set of measures and some some set of instruments, some set of measurement precisions. I think that's perfectly fine. And then saying, okay, well, we're not doing fundamental physics when we're doing this, talk about entropy. I think that's perfectly fine. It bothers people because entropy increase is supposed to be one of the fundamental laws of the universe and is not supposed to depend on things that aren't there in the fundamental physics. If you're, but that just might be the right answer. Right? Like thermodynamics is not a fundamental theory, right? Now, another thing you could say is, well, what really matters is, if I'm thinking about this as a resource theory, a distinction between macrostates, well, I'm going to pay attention to distinctions if they make a difference to what I can do with them, and not if they don't. So, if all the molecules are on one, so if I tell you how many molecules are on one side of the box and how many molecules are on the other, that's really useful to know because I can use that to expand one side or another. That's good to know. If all I've got is a piston that can expand the things in bulk and I don't have the means to manipulate things at the micro level, you tell me anything beyond that, you tell me the exact microstate, it doesn't affect what I can do with it, right? It doesn't affect what I can get out of it. Yeah. And this is something that a lot of people misunderstand about Maxwell's Demon example. The Demon example was meant to illustrate the dependence of thermodynamic concepts like entropy on means of manipulation available.
Mm-hmm.
Like so, in the first appearance of what we now call Maxwell's Demon was a letter from Maxwell to his friend Peter Guthrie Tate, who was writing a sketch of thermodynamics. And Maxwell said, you might want to pick a hole in the second law, because he's saying the second law, if the kinetic theory of gas is true, needs to be modified. And imagine some little being that could manipulate molecules individually, or imagine that he's got a little trapdoor in between the compartments of the.
I'll place a video on screen about this.
Yeah. Imagine that you've got gas in a box divided into two compartments, and there's a little trap door, and the demon can manipulate the door and let the faster molecules go one way and the slower molecules go another way. Well, that demon could, without expenditure of work, or more minimal expenditure of work, create big pressure or temperature differences that now we as macroscopic beings could exploit. And the moral of the story, according to Maxwell, is that the second law of thermodynamics is a statistical generalization, which is applicable only to situations where you're dealing with large numbers of molecules in bulk. And when he says statistical generalization, he's expecting his readers to be familiar with the sorts of statistical generalizations that the social sciences are coming up with, right? Like things like numbers of murders per capita per year, say. And if you think about it, there actually is a nice analogy. So if you keep sort of the macro level conditions the same, the broad scale socioeconomic conditions the same, then plausibly you're going to get a fairly stable number of murders per capita per year in a given situation. But if you could. Imagine a team of psychologists going in and talking to people if they had the ability to identify people who were at risk for committing murder or something like that, and talk to them and deal with them. If they could deal with the people on an individual scale, then you might be able to change that per capita per murder. Right? No, per capita murders per capita. Right? And so, but so what Matsu's saying is this daemon would be able to do what is at present impossible for us, because we do not have the abilities to manipulate things at the molecular level. He didn't think, the way he put it made it clear that he didn't think there's any fundamental law of physics that would prevent further technological developments from getting to the point where we could do this.
Yes.
Right. Now, as a matter of fact, he didn't really see this, but if you now include the demon, make the demon operate in a cycle, like so the demon, whatever it does, has to reset itself at the end of each iteration of whatever it's doing, then it actually is a consequence of the laws of physics, both classical and quantum, that on average the demon can't break the second law of thermodynamics, because like the classical case would be if you take the operation of, take the demon plus the whole system as an isolated system.
Yes, yes.
If the demon can operate in a cycle while reliably, putting all the molecules in the left side of the box, that is incompatible with Hamiltonian evolution, which conserves phase space volume. Like you'd be able to take a system that you would actually be able to reduce the volume of phase space occupied with the system. And there's something similar in quantum mechanics where you've got if you've got the whole system involving isolated evolution, then you've got, you can't take something that's initially spread out over a big subspace, a Hilbert space, and put it into a small subspace. And so actually, Maxwell didn't realize that if you require the demon to act in a cycle, then, but there's theorems to the effect of both classical and quantum mechanics, that the demon cannot reliably and continually do this. Right.
Precisely. What do you mean when you say that the demon acts in a cycle?
The demon has to end up in the same physical state it started out with.
Okay, why do you have to do that? I imagine that, look, if the demon has a brain and is opening and closing this door, then the brain changes.
Yeah. Yeah, right. So here's what people were thinking, and you're right to talk about the brain, and people have given simple models of this as like not a creature with a brain, but maybe a little device with like a memory device or something like that. Yeah.
Yeah.
So that the idea is that if the demon has some kind of memory storage, okay, then and if it never ever erases, and if it's just so it always remembers what it did on previous iterations and never ever erases anything, eventually it's just going to run out of memory. So it can't keep on doing this forever and ever and ever. And if it has to act in a cycle, if it has to eventually erase the memory, then there's actually a entropy cost associated with erasing the memory, and that's sometimes known as Landauer's principle.
Yeah.
And it really is just basically a consequence of what I just said, that if you require the daemon to act in a cycle, then it can't consistently and reliably violate the second law. So if I don't require the daemon to act in a cycle, then yeah, what it can do is, think about that blank memory as a resource. And it's doing this, and eventually it uses up that resource and hands you this box with a higher pressure on one side than others and said, okay, good, now you can use that to raise a piston or something like that. Okay, all you did was you took a resource and you converted it to another resource. You didn't actually violate the second law.
Yes, I see. Okay.
So you actually have to think about that memory reserve, that blank memory reserve, as having a entropy of its own, which so a memory which is just blank, or maybe full of all zeros, on this view has a lower entropy than a memory that's randomly populated by ones and zeros.
Okay, so let me see if I got this. There are two cases. Either it operates on a cycle or it doesn't. If it doesn't, it's going to use up a resource, in which case you still have a resource state. If it does operate on a cycle, then fundamentally you'll be shrinking phase space. Now, I know that most physical systems shrink phase space because there's some friction and so on, but at a fundamental level, you don't shrink phase space. Sorry, you don't shrink the volume you initially started with in phase space.
Absolutely, yeah. So when you've got a dissipative system, like something that's friction, right? Then you write down equations of motion, and it will go from everything in this original version of space will go to that, right? But that's because we're not actually thinking that system is an isolated system. Like it's in contact with something that's a source of friction, right? And if you include everything, like the pendulum that's going back and forth and dissipated, and whatever medium it is that's the source of friction, and you think of all that as undergoing isolated evolution, and you think, okay, ordinary Hamiltonian dynamics is going to apply, then that system as a whole is not going to shrink phase space. What's happening is, as the pendulum is damped and it goes in, across a smaller region of phase space, it's heating up the environment, warming it up, and basically it's transferring energy to the environment, increasing its entropy. Yeah.
So I have some funny questions for you.
Okay. All right. Good. I can't promise the answers are going to be funny.
Okay. Well, you're an expert in quantum mechanics and quantum field theory, and I'd like to talk to you about that next time in person because you live actually close by. So hopefully we get to meet up shortly.
For my colleagues in Europe, London, Ontario, and Toronto, Ontario count as close. My colleagues in the Netherlands always find it funny when I say things like that.
Nice. So there's a Heisenberg cut that's often referenced when it comes to the measurement problem.
Right.
Now, is the partitioning of macrostates, is there an analogy of that as to what we think of as a macrostate versus a microstate and the Heisenberg cut, the measurement problem? Or are these two separate issues?
Nice.
That's a good question. And I don't really have to think about, I sort of see where you're getting at, where prima facie there might be a connection, but I'm not seeing exactly what the connection might be. And it's not obviously wrong. So I would have to think about that. Yeah. There might be, actually. Yeah.
My second funny question is the universe an isolated system?
Is the universe an isolated system? Can we even talk about the universe as a whole? Presumably, yes. If you actually mean yes, everything in the universe is. If you literally mean universe is everything there is, then
it seems tautologically the case.
Right. However, another question is, does the universe as a whole obey the sorts of laws that we usually think of applicable to isolated systems? And here's why this is a genuine question, is it might be that, okay, for relatively small systems that we can actually isolate, the physics we apply to isolated systems applies, but when things are big enough, that doesn't actually apply. And what I mean by that is, in quantum mechanics, when you're asking, is a universe an isolated system, what you usually mean is it evolves according to whatever the appropriate analog of the Schrödinger equation is, and that can be represented by a family of unitary operators, and that preserves Hilbert space norm, and so it can't start out in, say, a small subspace of Hilbert space and go to bigger, right? But people who take dynamical collapse theories seriously think that actually this isolated Schrödinger evolution that we apply to sort of systems in the lab that we isolate is actually an idealization and not quite right? And that if you have systems that meet certain criteria, either they have enough particles or they involve displacements of large masses, then actually the physical law is a different one that isn't the law that we usually think of as isolated, and in fact mathematically mimics the sort of laws that we use for systems that aren't isolated. As you know, because I know you've talked to people about this, there are dynamic collapse theories, right, which modify the usual Schrödinger equation. And basically, the origin of those was, people are studying evolution of non-isolated systems and saying, okay, here's what happens to the state of the system if it's, say, in contact with the heat bath or something like that. And then saying, well, let's just imagine that something of this form or a similar form actually is the fundamental law. Okay? In which case, it'll still be tautologically, if that's right, it'll still be tautologically. Tautologously. That's what word I want.
Yeah, whatever.
Yeah, okay. If that's the case, it'll still be a tautology that the universe is isolated. But it might be that the way the universe as a whole evolves is as if it's continually being monitored by some external measurer. Yeah.
Okay, my other funny question is, it's often said that at some point we'll reach the heat death of the universe and that we won't be able to do anything even if we're supposing that we're around or whatever is our descendants.
Yeah.
Now, do you imagine that to be the case? Because if we're thinking in terms of a resource theory, then I could imagine that there would be certain questions that would be more important to us, that would be different to us, to whatever our descendants are. Maybe they are able to utilize a system with more precision.
Absolutely. Like the way we actually calculate entropy is, and this is something that's not often emphasized in textbooks, is relative to a certain set of parameters that we think we're interested in or we're going to manipulate. And for example, if I want to calculate the entropy of some standard volume of gas, the question is, do I count samples of gas with different isotope ratios differently. And as long as I'm only dealing with things chemically, it doesn't matter like how much of my oxygen is one isotope and how much it doesn't. If I'm dealing with nuclear reactions or if I've got some way to separate out things according to their mass, then that actually might be something. And so I might want to include that in the entropy calculations. So there's a sense in which entropy is relative to what is it you're going to manipulate. However, when people are talking about the heat death, well, no matter what it is that that you want to do, the natural tendency for things is towards left to themselves is towards diminished ability to do that, right? So eventually, and it was really in the 19th century that people started talking about the heat death of the universe. Kelvin himself wrote a article called "On a Universal Tendency Towards Dissipation of Energy." And so what is going to happen if things just keep going is the sun's going to burn out and okay, pretty much anything that we want to do here on Earth, like no matter what your goals are or your means of manipulation,
What's your name?
it
Hatos.
involves some kind of entropy difference that
Hatos.
ultimately traces
Okay, nice to
from
meet
the
you. My
fact
name's
that
Alex.
on one side of us we've got
Alex,
this high
nice to meet you. Let me.
Nice to meet you, bro. Nice to meet you. Good.
Опа. Сразу с коронок.
Да, а ты что, русский понимаешь?
Чуть-чуть.
А, чуть-чуть, хорошо. Окей. А почему? Ты
Почему?
учил или... Ну, русский язык ты почему знаешь? Ты учил
Родился
или...
таким, да, родился.
А, родился? Ты в России родился, что ли? Как я понял.
Почти.
А, почти, ладно, хорошо. Да сколько можно-то, а?
Так делай что-нибудь с этим.
Да, нормально.
Ай-яй-яй-яй.
Вот.
Ай-яй-яй.
Ой, я думаю, попал. Там мне показалось.
Опа. Опа.
Вот.
А ты через VPN?
Да. У
Ага.
нас не работает игра, ну, без VPN.
Ага.
Заблокировали все, сволочи.
Ну, это временно.
Я что-то сомневаюсь.
Просто что у нас как бы коннект должен быть как бы в 2-3 раза короче, но тебе приходится через какую-то европейскую фигню, блин, коннектиться. Пишет, что connection прямой, ну типа 90 миллисекунд, то есть обалдеть.
Да. Вот раньше, когда работал без VPN, конечно, прям вообще все идеально было. А сейчас,
А
знаешь,
давно
многие жалуются.
прекратила? Это сейчас то,
Да,
что происходит, да?
да.
Ага.
Этот, как его... Я заметил, многие жалуются, что у меня аватар дерганый.
Ну,
Есть такое?
бывает. Ну, бывает. И у
Мгм.
разных людей, причем у меня у самого как будто каждый день по-разному все. Просто,
Ну вот,
блин,
вот. А ты откуда, кстати?
ну, 404.
Из Украины.
Мгм.
Понял, понял. Хорошо.
Эти посредники, блин, коннекшн для нас держат, понимаешь?
Да-да. Спасибо, ладно, спасибо за игру, удачи, пока.
Good game.
Temperature source of low entropy energy, and on the other side we've got this low temperature empty space that we can radiate stuff back to. And okay, eventually that's going to run out. Um, even if you have more subtle ways of manipulating things, eventually everything's going to decay into black holes, and eventually, no matter what
Sure.
your goals are, and no matter what means you have manipulation, eventually things are going to run out and just stay that way forever, unless Roger Penrose is right about his conformal cyclical cosmology. When after that happens, then things get restarted. Okay,
Mhm.
but like so that's true. But honestly, we're talking like absurdly long timescales, like billions and billions of years. So I think we should be more worried about whether what are things going to be like for people on Earth in the next few centuries. Right? That is something that we can do something about. Right. And what's going to happen on this time scale of millions and billions of years is actually hard for us to wrap our heads around it. So, like some people find this, heat death of the universe is sort of depressing, and sometimes even people even say, okay, this makes everything meaningless.
Mm.
Well, you know what? You all, you've known most of your life you're going to die eventually, right? And you've got a certain limited amount of time to do stuff with, right? And do what you can with it while you have it. Do what make the best of the time that you have, right? And that applies on the human time scale. And I think the same thing we say. Suppose the human species is only going to be around for another million years. Well, I would say to that species, make the best of what you can with the time you have, right? So actually, I don't find it depressing. Uh, I mean, I do get occasionally, like, everyone has to deal with the fact that you and everyone else that you know is mortal, and you're not you have a finite lifespan. I do,
Oh, мгм. Ай-яй-яй-яй. Блин, соберись. Ух. Бля. Ух, повезло. Ух. Оп. Ох, хорошо. Ой, нестабильный какой-то пошел. Угу. Ух.
Yeah, it's hard not to have feelings about that. I find it difficult to actually have any emotions or feelings about what's going to happen in a billion years. Right? Yeah.
Disorder.
Disorder, entropy. Yeah.
Disorder is a word that we haven't said.
Yeah.
And it's something that many people in the popular press, when speaking about
Yeah.
entropy, make an equivalence between entropy and disorder.
Yeah.
What's wrong about that?
Like, you have to be careful about what you mean about order and disorder, right? And so there's a real sense in which if I've got a box of gas and there's a partition and all the gases on one side and none on the other, that is a more
Hey,
ordered
what's up?
state than if the
Sensei.
partition is out and there's gases all over the
Have a
place.
nice match, man. Good luck.
Ай-яй-яй. М-м. Мгм. Ай-яй-яй-яй.
Oh, nice.
Ай-яй-яй-яй.
Wow.
Бим. Мгм. Ай-яй-яй-яй. Блять.
Oof. Wow.
Ай-яй-яй-яй-яй.
Sorry.
Lucky. Блять.
Sorry. Wow.
Secret sauce.
Sorry.
Fuck. Фуф.
Sorry.
Ебанешься. Ей.
What? You're the first one who's ever done that on that serve. What the fuck? Nice.
No. Again?
Nice, man. No, sorry, man. Sorry, I
Okay.
have to go.
Тут какой-то not experienced guy какой-то. First time. Мы таких, блин, сделаем. Мяк. И все. Easy cheesy. Опа. Пропала вибрация. Бляха-муха. Надо перезагружать. Пиздец. Капста. Да бля, я не чувствую эту херню. Капец какой-то. Какая хуйня. Бля, я тупо не чувствую тут говно это. Блядский теннис. Ай-яй-яй-яй-яй. Это пиздец. Говнище. Говнище, блядь. Да ну в пизду. Сука, говна кусок, блядь. Это из-за того, что ёбнул по столу, блядский, сука, нахуй, блядь, окружающий мир. Ебать. Сука, мразь. Отстой. Просто отстой, блядь. Хуйня. Надо шлем перезагружать. Днище. Угу. Так. Фух. Чё так поднимает? Вот так вот. Ай-яй-яй-яй-яй. Ой. Ай-яй-яй. Ага. Да что такое? Фух, блин. Опасный. Ай-яй-яй-яй-яй. Руку. Да. Началось. Бля, вот криворукий. Не беручка. Ай-ой-ой. Ай-ой-ой-ой-ой. Воу. Ай-ой-ой-ой. Вот так вот. Ух ты. Ого. Повезло. Ай-яй-яй-яй. Так. Блин, зафиксировали. Пум-пум-пум-пум-пум-пум. Ага, еще один. Я думал, я уже выиграл. Намылился уже сматываться. А я чуть не проиграл. Ай, криворукий. Блять. Ну, хоть так. Сука, опять сейчас пиздец будет этому контроллеру. Да заебало. Блять. Сука. Надо тебе этот угол, блять, было трогать, блядский. В пизду. Блять, тупица, сука, ёбаная, нахуй. Заебет, блять. С этими столами, блять. Тварь. Пум-пум. Пу-пу-пум. Пум-пум. Пу-пу-пу-пу-пум. Опа. Пу-пу-пу-пум. Пум. Опа. Ай-яй-яй-яй-яй. Бля. Да ну дядина. Ай-яй-яй-яй. Мяу. Бывает. Мяу. Опа. Ай-яй-яй. Ай-ё. Мгм. Да что ж такое? Мгм. Ай-яй-яй. Ух. Ой. Сто 90. Nah, it's too high. Ему-то похер, блин. Он выкарабкается. Соточка. Тю. Угу. Ой. Угу. Ух ты. Угу. Угу. Ух, повезло. Ай-яй-яй. Ай-ё. Не хочет что-то играть. Пум-пум-пум-пум. Пуру-пум-пум-пум-пум. Па-да-дам-пам, па-да-да-да-дам. Ай-яй-яй. Мгм. Упс. Ай-яй-яй-яй-яй-яй. Опа. Блин. А! Ай-яй-яй-яй-яй. Ой, ё. Ай-яй-яй. Ой, сорямба. Йоу. Ух ты! До следующих встреч. Не стали продлевать.
And there's a and one way of thinking about that is that if the gas is indeed allowed to roam freely, it could spontaneously end up in one side of the box, but that corresponds to a very, very small region of its phase space. Right? And so the idea is that there are certain kinds of states that we find to be ordered, and those just are like a small percentage of all the possible states. Right? And there is a sense in which entropy is a measure of disorder. So what you're doing, when you're let's say I'm generating heat by friction, like I'm grinding this cannon bore, right? There's a sense in which I've got some regular ordered motion. I've got this thing going around like that, and I'm taking energy from that ordered motion, and I'm transferring it to the iron in the cannon, which is manifested as sort of higgledy-piggledy motion molecules. I think what's not right about that is that not everything that we would intuitively think of as distinction between order and disorder is actually corresponds to a distinction in energy. I'm sorry, not everything that
Entropy,
in
right,
entropy,
right.
Yeah. So if
The easiest way that I think about it is a coffee cup, and initially it's black
Yeah.
with
it's a
black
pidor.
coffee inside.
Yeah.
And then you pour some milk,
Yeah.
and then there's all this turbulence, and you'd say, oh, that's extremely disordered, and so you stir it,
Right.
and then you're like, oh, wow, now it's extremely
Right.
ordered, but it actually has the highest entropy.
Yeah, right. Yeah. So I mean that's a really good example, because there are some things that seem more disordered to us that are actually lower entropy, and that's a really good example. You've got
Да ёбаный, блядь.
before the milk. It's actually better if it's cream, because the cream can can take some time to sort of dissolve, to disperse, right?
Ah,
Yeah.
okay.
So if I've got if I take some thick cream and put in the coffee cup, I might have these swirls of cream in there, right? And that seems
Давай,
can be very
подавай свою
turbulent and
хуйню,
disordered,
блядь.
and then it settles down to a situation where the cream is evenly distributed, and that is a higher entropy state than
Чертила,
the
блядь.
intermediate state, but it seems to us like a simpler state, right? More. And so that's why it's important to think actually in terms of order and disorder on the molecular level, and also
Хуесос, блядь.
not everything that we think of as more or less ordered really corresponds to entropy differences. So when gravity is comes into play, the natural tendency, if I've got a bunch of gas spread out in interstellar space, the natural tendency for it is for the gravitationally clump together.
Без
And
руки,
so the
блядь.
clumpy,
Yes, yeah.
right? And so a bunch of gas uniformly spread out, which clumps together and forms a star, that's actually an entropy increasing process, even though intuitively you might think
И
the
нахуй,
end
блядь.
state is more ordered than the initial state. And so if you're thinking sort of as a rough
Уебан,
and ready
сука.
way, there is a sense in which molecular disorder and entropy go together. It's not a reliable guide. And I think what sometimes people think
Иди в
about
пизду, блядь.
when they mean ordering disorder is actually something a bit different in what people sometimes call complexity. So Sean Carroll was here sometime last year, and he was talking about origins of complexity. And when people who study complexity, that is another really precise difference, is that tend to say is neither the minimum nor
Гнилой
maximum
пидор, блядь,
entropy states
французский.
are the most complex. Like there's a sense in
Right, okay.
right. Yeah.
Something we didn't speak about that comes to mind is ergodicity.
Ergodicity, yeah.
So, are the laws of physics ergodic? Is that a well-defined statement? And also, please define what ergodic is.
Yeah, so classically, ergodicity pertains to a system confined to a finite region of its state space and undergoing isolated evolution. And to be ergodic means that take virtually any initial condition you want and take any finite region of phase space, eventually that initial condition ends up in that region of phase space. And for actual physical systems, it's very difficult to decide. If I hand you, like, here's a law of dynamics and say, is this ergodic or not? It's actually very mathematically difficult problem to actually decide, right? So, and of course, that was a classical definition. The laws of physics deep down we know aren't classical. In quantum mechanics, basically, that definition of ergodicity, like a state, just doesn't really apply. There are things that are called quantum ergodicity theorems, which basically have the effect that any state can be approached as closely as possible. Are the actual laws of physics like if I actually took, say, a box of gas and somehow or another isolated it and let it go according to ordinary quantum evolution, there is a sense in which something like ergodicity applies in that if you look at sufficiently long time averages, then the amount of time it'll spend in a given subspace will be, for almost all initial states, proportional to the dimension of that subspace. I'm not sure that, something of that sort of flavor often comes in when people are trying to prove equilibration results. So you want, what we haven't talked about is this sort of process of you leave something alone. It starts out from a far equilibrium state, and then it goes to a equilibrium state, and that's sometimes called the minus first law of thermodynamics.
Right.
Yeah, we haven't talked about that, and one of the reasons we haven't talked about that is that
Пиздец, блядь.
it's hard to say anything really precise about that because there's various results, and it's not always clear. You can get nice, clean mathematical results whose physical significance for actual systems is a bit obscure. And then you get sort of plausibility arguments for actual physical systems. And I actually think that ergodicity, in any sense, which really has to do with infinite long-term average behavior, really isn't the right question. Because what I want to know, if I pour the milk in the coffee cup, right? Not what it's going to do on average if you left it alone, isolated for all eternity, but what is it going to do in the next few minutes? Like, you want to know actually what's going to happen in finite timescales. So statistical mechanics textbooks are divided on whether ergodicity is actually important for statistical mechanics. Some will say, okay, this ergodic hypothesis is at the root of statistical mechanics, the hypothesis that actual systems are ergodic. And then others will say, oh, there's all this really nice mathematical work having to do with ergodicity and is completely irrelevant to statistical mechanics.
Okay, here with the cream and the coffee cup, we only have to wait a few minutes. And so it's not infinite, it's not t goes to infinity. However, Nima Arkani Hamed also talks about how with particle physics occurs at the boundary. Why? Because in the math, we're scattering from minus infinity to plus infinity. And yes, it takes place in just a few milliseconds or a few seconds or what have you, but for the calculations, we just use infinity. Now, he seems to be using the opposite argument that you just used. So would you be able to convince him, no, Nima, it's actually not happening at infinity. It's not at the boundary.
Well, yeah, so when he says happening at infinity, I think one thing you have to realize is that when physicists say infinity, what they often mean isn't literally infinity, but large enough that it doesn't really matter how big it is. There's a nice book called Understanding the Infinite by a philosopher named Sean Levine. And he
Aiyo.
introduces what he calls the theory of zillions. And a zillion is a technical term.
I see.
A zillion is a number
Blah.
that's so big it doesn't really matter how big it is.
Okay.
Right? So it's context dependent, right? And if you think about it, that's sort of how we use the word. Like if I say, if someone says, Wayne, you go to conferences so much, why don't you just buy a Learjet, right? And I would say, well, that costs like $1 zillion, right? I have no idea what a Learjet costs, right? But I do know that whatever that cost is so far beyond my own financial resources. It doesn't really matter exactly how big it is, right? And one of my colleagues said, we have to realize in quantum field theory, asymptotic infinity is like 5 meters, right? Because what you do when you're doing these scattering experiments, right? What you're doing is there's a relatively small scattering region, right? And far enough from that scattering region, the field is effectively free, right? And then so you're basically taking in and out states as if they're free fields. You're doing your calculation and you're calculating scatterings, cross sections, etc. for effectively free fields.
Good game.
And really, what you'll say ad infinity, and mathematically you might take the limit as things go to infinity because that's a nice, clean physical result. But what you really mean is this is a good approximation far enough from the scattering region that the interactions can be neglected. Right? And I think that that's what he means when he says the interesting stuff happens at infinity, right? And so with the with something like that, if I've got an interaction and I have a sense of how fast the interaction falls off its distance, I can get a sense of how far I have to be from the scattering region to say, okay, these are effectively free fields, right? What we want from equilibration results is some result about, okay, how long do I have to wait till I say, okay, yeah, we're effectively at infinity because the thing has equilibrated. And that's what you're trying to get out of the equilibration results. And it's not as simple because it's not as simple as in the quantum case, because in the quantum case, you've got these distance-dependent forces, and you know how fast they drop off. And what you're trying to find out in the equilibration case is, well, how fast does something equilibrate? How fast does it get to the point where I can basically ignore the fact that it was out of equilibrium at the beginning? Yeah.
Okay, I have another funny question.
Yes, okay.
So Natty Seiberg said that one of the ways that an indicator for quantum field theory being on shaky foundations or not firm foundations is that we teach quantum field theory differently. So almost no textbook in quantum field theory is the same, and almost no course is the same. So some person may say, let's start with scalar fields and then add interactions. And then some person may say, well, let's start with all free fields and then add interactions, and others a functional approach, and so on and so on. So that's not a controversial statement, that QFT isn't firm. But what I'm wondering is, do you personally, Wayne, have an idea as to a field or a subfield, a particular subject in physics that other people think, no, this is well understood, but you think, actually, there is trouble here?
Well, I think that statistical mechanics is a case in point, because people, textbooks are written to give the impression that we understand everything and this is all worked out. And if you actually go from one textbook to another, you'll find very different approaches. Like in quantum field theory, everyone knows that there's different approaches, and statistical mechanics is sort of swept under the rug. And so that is one case where I think there are real questions about the rationale for certain kind of methods that got kind of swept under the rug. And the thing about thermodynamics is thermodynamics is sort of even though we don't think of it as fundamental cutting-edge science, it's got its roots in 19th century physics. Different thermodynamics textbooks will take very different approaches. And I think that the root of that is that there's sort of different conceptions about what thermodynamics is supposed to be. So one conception is what I call the resource theoretic conception, where it really is about what you can do with various things. But what people usually want from a thermodynamics textbook, especially if it's preparing people for doing chemical thermodynamics, is you want to figure out what the equilibrium states of a system are, and those are the ones that maximize entropy. And a textbook with that orientation will tend to minimize talk of manipulations and doing work and things like that, and treat entropy as if it's simply a property of matter, like mass and other things. Yeah. I think in a lot of areas, actually the textbook tradition will sometimes obscure different ways of thinking about the theory. And so the question is, like, in what areas are there where there's a sort of settled, everyone agrees on how to do this? I guess classical electrodynamics. Every single textbook in existence is a copy of J.D. Jackson's book. And I think it is a that's possible because there is this theory that we call classical electrodynamics that we think has been superseded by quantum electrodynamics. So we can all agree on what classical electrodynamics is because it's not. It's in a sense a closed book. Right? And quantum field theory is a continuing area of active research, and so one of the reasons for the different approaches in quantum field theory is we just don't have a good mathematical grip on the theory as we do other areas of physics, right? You write down a Lagrangian standard model Lagrangian, and is this a well-defined? You put in a cutoff, and if you let the cutoff go to infinity, you have blow-ups, which you have certain techniques for regulating. Is that telling us that the theory we wrote down actually isn't well-defined at all energies? And, or are these cutoffs that we're introducing just a calculational tool for getting at the consequences of a well-defined theory? I think that, as far as I understand it, and there are people who are much more on the literature, I actually think that that's still more or less an open question. And I think the standard view is it doesn't really matter whether the theory we're writing down is well-defined at all energies, because we think that it's an effective field theory valid at certain energies, and we really don't know what's going on beyond those energies.
But you don't buy that answer, or what?
No, I think that's right. So that's why we can get away with actually not knowing the answers whether the theory we write down is actually well-defined at all energies. Like, if that's your attitude, then it doesn't really matter whether it is. Yeah.
What's a lesson you learned too late?
What is a lesson I learned too late?
2 раза, пидорас.
And I'm assuming you want to know about physics and philosophy of physics and not about personal life.
Да, блядь, нахуй.
So this idea that what I've been saying about thermodynamics, that there's two different conceptions of what the theory is. But we have resource theory conception, and this other conception according to which it's more like mainstream physics. That took me a surprising amount of time to actually get clear in my own head about. But now I think it's really, it should be like one of the first things that anyone says when they're talking about thermodynamics. And as you know, I've given talks several times with the title "A Tale of Two Sciences, Both Called Thermodynamics." And really, it only is relatively recent years I saying, okay, that's the way I want to be thinking about that.
Now, many people watch this channel who are researchers in math, physics, computer science, so adjacent fields, and philosophers, and there's also lay people that watch. So I'm curious what advice you have that you give to your graduate students, but also advice that may apply to this wide gamut of people that watch.
Okay, I would say here's advice I give to my grad students when they're, and this will apply to like researchers in any field if they're just starting out or something like that, is when you're choosing what things to work on, what you should not do is look around and say, okay, what's the hot topic? What's the popular thing? And jump on the current bandwagon. And for two reasons. If you're doing something because you think it's popular and you're not particularly interested in it, well, if you're not interested in your work, there's just no way you're going to get anyone else interested in your work. Right? And also, if you're jumping on a bandwagon and then you're applying for jobs and you're submitting your things you've written, or you're submitting parts of your dissertation for publication, my experience as an editor, I was editor of a philosophy of physics journal for a number of years. My experience as an editor, when we get a paper which is the nth minor addition to a well-worn topic, the threshold for that being worth publishing is very, very high, because if you don't want to publish, even if what you're saying is correct, one of the things you're asking is, okay, if this is going to take up journal space, is this actually a significant advance over what's out there in the literature? And we're like, if something's a hot topic, then people are going to get tired of it fairly quick. So do something that you're interested in, but don't choose something just so narrow that like only 3 people are going to have an idea what you're talking about. So there's sort of a happy medium between choosing a research topic that some people are going to have some knowledge about, and jumping on the bandwagon and doing what everyone else is doing. Yeah. Yes.
Okay, so let's imagine you're speaking to your PhD and postdoc students who want to get a job in the field.
Right.
I imagine that at some point they have to maybe not jump on a bandwagon, but hitch a ride occasionally, because don't you have to get grants? Don't you have to be marketable?
Okay.
So how do you navigate that?
So my teacher, Abner Shimoni, I had the honor of working with him at Boston University when I was a grad student. One of the things he would say is, just as Aristotle taught us that ethical virtues are means between opposing vices, intellectual virtues are also means between opposing vices. And I think when you're choosing a research area, there's two opposing vices. One is choosing something that's such a niche area that only 3 people in the world are going to have any idea what you're talking about. And I think the other vice is jumping on a bandwagon and doing what everyone else is doing. And I think the reason I mentioned that other vice first is I think there's a mistaken impression out there that that's what you're supposed to do. That's what you should be doing. Right? And I think that that's a mistake. And this is based on my experience as an editor, and also talking to other people in the field who edit journals, and also talking in my experience as on panels that adjudicate grants and things like that, is sure, like if someone reading something and says, I have no idea what this is about, okay, that's a tough sell, right? But if you've got a dozen grant applications in front of you, and 10 of them are minor variants on the same thing, and what they're going to do is at best make a minor advance in a well-worn field, and another one is an interesting and promising research project that is worth doing but relatively unexplored, that's actually going to count in favor of the one that's worth doing and relatively unexplored. There's this idea that I think is just simply false, that there's a sort of groupthink and everyone wants to only give grants to what they think everyone else is doing. I think that that's just false. And in terms of getting jobs, let me tell you, this is a true story. Many, many years ago, we were hiring at the University of Western Ontario, and I was on the hiring committee, and we had a job ad which was fairly broad. And what had happened is in one of the areas of specialization that was included in the job ad, a big name philosopher had recently published a book that was getting a lot of attention. And what happened was everybody in the world did a grad seminar on this book. And I was sitting there reading these applications. This was back in the days when people actually sent us paper applications, and there's a file box with all the applications in it, and you take it into your office after hours, and you're going through it, right? And I was reading the writing sample of one candidate, and I read the opening paragraph, and going, didn't I just read this? I'm going, oh my God, one of our applicants has plagiarized the writing sample from another applicant. And then I went back and got that other file, and they were in fact different. But the opening paragraphs were almost word for word the same, because this was this issue that everyone was talking about, and there was a very standard way of setting up the issue.
I see.
So if you want people to actually confuse your writing sample with someone else's, then jump on a bandwagon.
Interesting. So this also applies to film and businesses in general. You don't want to be in the red, it's said to be, the red contested waters. You want to be in the blue ocean.
I'm not familiar with that terminology, but I'll believe you. Yeah, right. Yeah.
You just referenced, I could give you a personal lesson, but instead I'll give you a lesson that applies to philosophers and physicists. And that has me curious. What would be the personal lesson that you learned too late? And something not trivial, like, I should double bag my groceries.
Let's see.
Что такое?
Lesson in my personal life that I think I learned too late. If there are toxic people in your life, avoid them. Yeah. Be around people that you're comfortable around and you feel good around, and try to minimize your contact with the toxic people.
Thank you so much for spending so much time with me.
Well, thank you. I've really enjoyed this. Well, it's been 2 hours. It feels like it just flew by.
Yes, that's
right.
always a great sign.
Right.
In fact, in Harry Potter, I think there was a sands of time.
Бля,
And then
опять
Harry asks the professor, what is this? Because it was a different type of sands. And then the person said, it stands still when the conversation's engaging.
Oh, that's good.
больше ж
Actually, I
ничего
have another
не
life
читал.
lesson which I heard early in my life, but I am to this day not particularly.
Focus your attention on a spot. And when that spot has your full and complete attention, take a deep breath. Let it out. close your eyes. Close your eyes and relax. Relax. Listen to the sound of my voice and relax. Listen to the sound of my voice and allow every muscle in your body to relax. Listen to the sound of my voice and allow yourself to drift deeper and deeper into relaxation. For just a few minutes, let your mind go blank. Think of nothing. Just listen to the sound of my voice and relax. Relax. Pretend I'm filling this space with a warm, relaxing air. Breathe in and feel this relaxing air taking effect. With each breath, you feel yourself becoming very drowsy, very dreamy and relaxed. With each breath, allow yourself to drift deeper and deeper into relaxation. Feel the relaxation beginning at the bottom of your feet and gradually working upward until your entire body is relaxed.
Ай-яй-яй.
Imagine yourself on an escalator
Ух,
going down, down into relaxation.
good game.
Consider a fish.
Ух ты.
Is it a big fish? Is it a little fish? Is the fish in a box?
Ух ты.
Is the box a cardboard box? Consider yourself. Consider
Над столом, что ли?
yourself at home. Consider yourself part of the furniture. Consider yourself one of us. Whatever we've got, we share.
Ай-яй-яй.
you feel yourself going into a deep, deep state of relaxation. Let go and relax more and more. 10, 9, 8, 7, 6, 5. Deeper and deeper.
Deeper.
4, 3, 2, 1. Your whole body drifts deeper and deeper into relaxation. Deeply relaxed.
Угу. Да что такое? Ух, повезло. Ай-яй-яй. Ух.
Let's serve.
Ух! Вырвал зубами. Ух ты. Угу. Хорошо. Ай-ё. Еще?
Пошел нахуй, русопидор ебаный, сдохни от спида, мразь.
Лох. Ой, все, что ты можешь, это материться. Nice. Ага. О!